In today's lesson, we're going to take a look at the difference between endothermic and exothermic reactions. And before we even define these terms, you can look at some of the different parts of the word to give you an idea about what they're about. So for example, in endothermic, the prefix endo means in, and therm means heat. So it literally means heat coming in. As opposed to exothermic, the prefix exo means out, and therm once again means heat. So exothermic literally means heat coming out. So let's take a look at this in a little bit more detail to see what they're about. Okay, so before we get into it, we should first start off by defining what we mean by temperature, because there's some misconceptions with temperature. And so temperature is a measure of the average kinetic energy of the particles. So it has to do with the movement of the particles in a substance. And it's related to heat and thermal. There is a slight distinction, but you should get an idea that temperature is just measuring the average kinetic energy of a particle or substance. And we use a variety of units. In the US, we typically use degrees Fahrenheit to talk about temperature. In science and in most other countries, we use degrees Celsius. There's also another unit commonly used in science, and that's the Kelvin scale. So you should be familiar with Kelvin. And the formula that we can use to convert Celsius to Kelvin is seen here. So Kelvin is equal to whatever the degrees is in Celsius plus 273. Okay, and if we wanted to go from Celsius to Kelvin, then whatever the Kelvin is, we can just subtract 273 from it to get the degrees in Celsius. So it's a useful formula to know. Okay, so once again, what exactly is an endothermic reaction? So this occurs when there's a greater amount of energy that's required to break bonds in the reactants than there is to release the new bonds that are being formed. Or to put simply, it just means that energy is being absorbed. So this definition here has to do with the potential energy diagrams that we looked at a few weeks ago when we were talking about kinetics. Okay, and I gave a couple of examples here. So for this first example, if I have a single oxygen atom that's reacting with another single oxygen atom to produce an oxygen molecule, O2, this is going to be an endothermic reaction because energy has to be taken in, energy has to be absorbed in order to bond these two individual oxygen atoms. Okay. Another way of looking at endothermic reaction can be seen in this reaction here. If you have 2 moles of this sodium bicarbonate, which is basically baking soda, plus energy, that's going to produce sodium carbonate, which is this substance here, plus H2O water, which you should be familiar with, plus CO2, or carbon dioxide gas. The way this reaction is written here, it tells you that it's an endothermic reaction because the energy is written on the reactant side of the chemical reaction. Now, as opposed to an exothermic reaction, so that occurs when more energy is released during the product bond formation than is required to break the bonds. Or simply put, it means that energy is released in this case. So if I took the reverse reaction that we looked at before, if I took an oxygen molecule and I wanted to react to separate it into its individual oxygen atoms, that's going to be an exothermic process because energy has to be absorbed in order to break the bonds here in order to separate it into these two individual oxygen atoms. Okay. Another Another way of representing this in exothermic reaction can be seen in this chemical reaction down here. If you have CH4, which is methane gas, plus oxygen gas, this is a combustion reaction here, that's going to produce CO2, carbon dioxide gas, plus H2O, water vapor in the gas form, plus energy. Now this tells you that it's an exothermic reaction because the energy is written on the product side of this chemical reaction, indicating that energy is being released in this reaction. Okay. It's also important to note that energy in chemistry is typically measured in joules, J, or kilojoules, KJ. You may be familiar with calories. Calories is also another unit used to measure energy, but typically in chemistry we use this unit here of joules or kilojoules. Okay, so phase changes can either be categorized as an endothermic or exothermic process. Okay, so these following phase changes require energy, or they're endothermic, or in other words, energy has to be absorbed in order for these things to happen. So if something is melting, like a block of ice, if that's melting, if it's going from solid to liquid, that ice has to absorb heat energy in order to make the molecules move faster, to make it go from the solid state to the liquid state. So that's an endothermic process. The same thing for vaporization, or it could be described as evaporation or boiling. They all mean the same thing. When a liquid is turning into a gas, once again, energy has to be absorbed so that the substance can change its phase from a liquid to a gas. Okay, and then sublimation, when a solid goes to a gas, you saw this with some dry ice. Once again, energy has to be absorbed in order for that process to happen. Now, these three phase changes are exothermic processes, and they're going to release energy in the process. Okay, so if something is freezing, if it's going from a liquid to a solid, energy has to be released from the substance in order for this phase change to happen. The same thing in the case of condensation. When a gas is going to a liquid, energy needs to be released. And deposition, which is the opposite of sublimation, when a gas is turning into a solid, energy needs to be released for that process to happen. Okay, we also can represent some of these phase changes using some diagrams, like heating curves. So let's start off by defining heat. So heat is a form of energy that flows from a warmer substance to a cooler one. Okay, and if you look at this diagram here, you see it goes up, it stays steady, it goes up again, it stays steady, and it goes up once again. Now, what is this diagram showing? On the y-axis, it's showing the temperature, so we can measure that in degrees Celsius. And on the x-axis, it's showing heat. So what this is saying is that as heat is being applied to a substance, it's going to go from the solid state, that's what this portion of the gas represents, and then it's going to reach to a level where the line is going to be steady. This steady part here represents the point at which the solid is going to turn into a liquid. So this portion of the graph here represents the melting stage of the substance. It also represents the freezing if we're going in the opposite direction. Okay, and then once the substance melts, it's going to be in a liquid phase. So this portion of the graph here represents the liquid phase. But then eventually, it's going to reach a point where it's going to go from liquid to gas at a particular temperature. So this horizontal portion here represents that stage in which it's going from a liquid to a gas, or a gas to a liquid. When it goes from a liquid to a gas, we call it vaporization or boiling. When it goes from a gas to a liquid, we call it the condensation point. And then this final portion here represents when the substance is in the gas phase. So all of the flat parts, those are very important parts. Those are all the transitional parts. Okay, so that's the kinetic, it's telling you that the kinetic energy is basically staying the same, okay, as it's making its transition. And then this is just the same heating curve, but it's specifically showing it for water. Okay, so if you take a look at here, this part of the graph represents when the water is in solid form, when it's ice. And then if it absorbs enough heat to get to this point here, to 0 degrees, this is the melting point, or it's the freezing point for water when it's at this point. And if that substance absorbs enough energy, it's going to transition from the solid to the liquid phase. So this part of the line here represents the liquid phase. But if it absorbs enough energy, particularly when the energy level is at 100 degrees Celsius, it's going to once again transition from that liquid to the gas phase, which is referred to as the boiling point or the condensation point, depending on which direction you're looking at. And then this part of the graph represents when water is in gas form, is in water vapor. So it's important to note that the melting point is the same as the freezing point. So in other words, the temperature at which something melts is the same temperature at which something freezes. Okay, so water melts at 0 degrees. It also freezes at 0 degrees. And additionally, the boiling point of the substance is equal to the condensation point. So the same temperature at which something boils is the same temperature at which it condenses. So in the case of water, its boiling and condensation point is 100 degrees Celsius. Okay, so now we're going to take a look at a couple of problems on the devices or in your textbook. So I'm going to stop the video here. Thank you.